Hey guys, in this video I want to present to you a solution to USA TST 2024 problem 1. The statement is as follows. We are asked to find the smallest constant c such that for any natural number n and any sequence of n numbers a1 up to an that are positive real numbers but not integers, such that the sum of their inverses is equal to 1, we can do the following. We can find bi that are for each I either the floor of AI or the ceiling of AI, such that the sum of the inverses of bi is greater than 1 and bounded from above by c. The smallest example we can consider is for n is equal to 2, and I will take a look at the example where a1 and a2 are almost both equal to 2. So let's set a1 equal to 2 minus epsilon 1, where epsilon 1 is small, and a2 equal to 2 plus epsilon 2, such that our condition is satisfied. If we define c1 to be the ceiling of a1, then it is equal to 2, and in the same way, the ceiling of a2 is equal to 3. 1 over c1 plus 1 over c2 minus 1 is exactly equal to 1, which is not greater than 1. Therefore, in order to exceed this 1, we need to have a 1 over c1 minus 1, and we have 1 over c1 minus 1 plus 1 over c2 is equal to 4/3, which therefore yields that c is greater than or equal to 4 over 3. As I said, in this example we were forced to put a c1 minus 1 here. Since c1 is equal to 2, which is almost equal to a1, this increased our 1 divided by a1 by almost a half. The only reason why we don't get a 3/2 or something close to 3/2 in the end is because we lost lots by rounding a2 up to 3. Here I want to note that ci equal to 2 is the best possible case for us. As I said, we gain 1/2 by changing ci to ci minus 1. This motivates us to try to prove that 3 over 2, which is 1 plus a half, is an upper bound for c, which will be our first claim, that c is less than or equal to 3 over 2. So let us consider a natural number n and ai in this way, and we again define ci to be the ceiling of ai. Since the sum of 1 divided by ai is equal to 1 and the ai are not integers, we know that ai must be greater than 1. Therefore, ci is at least 2. This implies that 1 divided by ci minus 1 is less than or equal to 1 divided by ci plus a half, where equality is attained at ci equals 2. Let me note that ci minus 1 is equal to the floor of ai, since ai is not an integer. For the same reason, ai lies strictly between ci minus 1 and ci. Since we have a positive number of summons here, we conclude that the sum of 1 divided by ci is less than the sum of 1 divided by ai, which is 1, and this is again less than the sum of 1 divided by ci minus 1. Let us consider the following setup. We start by setting all bi equal to ci. They clearly do not satisfy our first inequality. Then we step by step decrease bi to ci minus 1 and stop whenever we exceed our value of 1. Using this first inequality, we will show that we don't exceed 3/2 at this step. To achieve this, let us first define f of k to be the sum of I going from 1 to k of 1 divided by ci minus 1 plus the sum of I going from k plus 1 to n of 1 over ci. Let L be minimal such that f of L is greater than 1. L is well defined because we have this inequality that tells us f of n is greater than 1. The first inequality now tells us that L is greater than or equal to 1. In conclusion, 1 is less than f of L, and we know that L is greater than or equal to 1. Due to this inequality, we can therefore bound f of L from above by f of L minus 1 plus a half. And due to the minimality of L, this is all at most 3 over 2. So we can always find a suitable choice for the bi such that these inequalities are true with 3/2 on the right. And that tells us that c is at most 3 over 2 as desired. To show that c equals 3 divided by 2, we will give a construction. And before we do that, let's take one more look at our initial example, where our problem was that we lost a lot by setting b2 equal to c2, which is 3 and thus much larger than 2 plus epsilon 2. In order to avoid this problem, we want to split up this a2 into lots of different ai's, such that we are not able to lose much by rounding. We have to be careful in doing this, because in order to really win our 1/2 to land us just at c equals 3 over 2, we have to make sure that every valid choice of the bi will have the 2 minus epsilon rounded down to 1. So as I said, we want to think of n as some large number, and then we set a1 particularly equal to a number that we call s, that is defined to be 2n over n plus 3. We define the other ai to be equal to t, which therefore has to be equal to 2n times n minus 1 divided by n minus 3 in order to make sure that this equation holds. Let's show that the ai are not integers. We start by proving that s is non-integer. If, on the other hand, n plus 3 divided 2n, then their GCD would be equal to n plus 3. But we know that this is nothing but the GCD of minus 6 and n plus 3, which is of course less than or equal to 6. If we choose n large enough, namely such that 6 is less than n plus 3, that is clearly not the case, so a1 would be not an integer. In the same way we can deal with t. The GCD of 2n times n minus 1 and n minus 3 equals, by Euclid's algorithm, the GCD of 4n, n minus 3, and this is nothing but the GCD of 12, n minus 3, which is less than or equal to 12, and again, if we choose n large enough, this will be less than n plus 3. In conclusion, if we let n be at least 16, then these variables ai satisfy all of our conditions. Firstly, notice that s lies strictly between 1 and 2. Now, to get a good lower bound on c, we need to prove that in order for this sum to be larger than 1, b1 has to be equal to 1. So we need to bound 1 over the floor of t minus 1 over t from above. This is less than 1 over t minus 1 minus 1 over t, which equals 1 over t times t minus 1. Notice that t is larger than 2n, n minus 3 over n minus 3, which equals 2n. And so this is less than 1 over 2n, 2n minus 1. Therefore, we can now get an upper bound on 1 divided by the ceiling of s plus n minus 1 over floor of t. Namely, 1 over ceiling of s is a half, which is just 1 over s minus 3 divided by 2n. So all of this is less than 1, which is the value of the original sum of inverses, minus 3 over 2n. And then we get a plus n minus 1 divided by 2n, 2n minus 1. n minus 1 is less than n minus 1/2, so this is less than 1 minus 3 over 2n plus 1 over 4n, which is clearly less than 1. For the other direction, we need to prove that 1 over the ceiling of t minus 1 over t is not too negative. This is greater than 1 over t plus 1 minus 1 over t, which is just equal to minus 1 divided by t times t plus 1. Here, we use again the fact that t is large to obtain that this is greater than negative 1 over 2n, 2n plus 1. In conclusion, 1 over the floor of s, which is 1, plus n minus 1 divided by the ceiling of t is greater than 1 plus n minus 3 over 2n, which is 1 minus 1 over s, minus n minus 1 over 2n, 2n plus 1. For n large enough, this gets arbitrarily close to 3 over 2, from which we can conclude that c must be at least 3 over 2, which is exactly what we wanted to show. Now we know that c is exactly equal to 3/2, and we are done.